Hello friends and welcome to this video. In this video we will be diving into the fascinating world of image segmentation using UNETR, a powerful neural network architecture. Image segmentation is a crucial task in computer vision, allowing us to identify and classify different objects within an image. UNET R or UNet Transformer is a specialized architecture for medical image segmentation. It uses a pure transformer as the encoder, focusing on learning sequence representation from the input to capture global multiscale information. The encoder connects directly to a decoder through skip connections, forming a unit-like structure and producing the ultimate semantic segmentation output. In this entire tutorial, I'll guide you step by step on how to train UNET-R on your own image segmentation dataset. So whether you are new to the field or looking to enhance your skills, you are in the right place. So let's now jump into the coding part. So let's start by taking a look at the folder structure. So here we have first folder called hair segmentation. So this is our dataset which we're going to use in this video, and after that we have four files. Our first file is matrix.py and it contains two functions, and these are dice coefficient and dice loss. After that we have test.py and train.py, and inside both these files we're going to write the code for training and testing. After that we have the implementation of UNET-R in 2D. Okay, initially this was not in 2D. This architecture was designed for volumetric image segmentation, but we are using it for 2D. Now let's take a look at the data set, and the images we have in this data set are around 29,000. Here you can see. So this is a really good data set if you see size of it. So just wait, let me stop and load these images again. So take a bit of time. Here you can see all the samples that contain human faces, and we need to segment their hairs. And these are the masks. You can see here. Okay, now you can see all the masks. So this is the task for this video that we are going to do human hair segmentation using UNET-R. So let's start. So first of all, we'll take a look at the this UNET-R architecture. So most of you are saying that please make a video on training it. So this is the video, and some of you even complain about that there is some error. I think it is usually attached when you have when you increase or decrease the patch size. Okay, so default value is 16, and I think this architecture, the way it is designed, it work with a patch size of 16 by 16. Even I have tried to work on it to change patch size, but it also gave me an error. So what I've done, I've made few changes in this architecture. I've added few layers to accommodate size. So here we have some deconv layer which uses transpose convolution to upsample the feature map, and we also have some pooling layer to decrease the feature maps accordingly so that we can accommodate different patch size. So I'll upload this code, and maybe you can use this code. So what I'll do, I'll show you how it works for different patch size. Let's say now we are taking a patch size of 1. I hope it should work because I've already checked it and made few changes. Here you can see it's working fine. You can see this is our mask. Now let's change patch size to 4. Let's say how it works. Okay, it's working. Let's change it to 16. So we'll check with different patch sizes and see if it works or not. It's working. Let's check it for 64. So you can apply any patch size. I think it should be of 2 raised to the power I, and I can be anything like maybe 1, 2, 3, anything. So it's working with all patch size. Let's say patch size is equals to image size. Let's say if it works. So this means we have only one patch size that is equal to the image. So it even work with a patch size that is equal to the image size. So now this code is working fine. So one major problem is solved. Now we'll start writing code to train our UNETR architecture. So first of all, we'll import all the libraries which we require. And here you can see we are using TensorFlow as our main library, and rest all the function would help us to train our architecture only. So first of all, we will write all the configuration that will be required by our UNETR architecture. Here you can see we have the image size, number of channel, number of layer, and rest of the thing which we require. And I have set them according to me only. So you can check the vision transformer paper or UNETR paper and set these values accordingly. And I've also decreased this number of channels, okay, so that it is easy to train. Next, we have a function which would help us to create folders. So here this function, that is create underscore dir, would take this path, and if that path does not exist, then it's going to create that path or that folder. Now we'll move on to the main function from where the execution start, and we'll seed the environment first. Okay, next we're gonna have a folder which would help us to store our weight file. So we have a folder called files, and within this folder we're gonna save our weight file. Next we have few hyperparameters. So first of all, we have batch size of 8. You can set this batch size accordingly. Next we have a learning rate of 0.1, number of epoch to 500. So I've set this large value, but we are not going to surely train up till this, because I am going to use early stopping as a mechanism to stop the training. This is just a large value. Next we have the path for our weight file and path for our CSV file, and we're going to use them during our training. So next we need to set the path for our data set, and we're going to build a function for loading and splitting the data set. So here is our function load underscore data set, and this is the path, and it's going to give you training images mask, validation images mask, and testing images and mask. So now let's move on to the implementation of this function. So here is the complete function, and you take your dataset path and have a split that is equals to 0.1. So this is its default value. So 0.1 basically means that 80% of the data would be used for training, and rest 20% would be equally divided between validation and the testing. So first of all, we load all the images and mask, and for that task we are using globe function which take a specific path, and inside this path we specified star.jpg. So this means load all the files, that is images file, with any name, but they should end with .jpg, and same goes with the mask, just that it's having an extension of .png. So now we have list of images a path and list of mask path, and we sort these list. So if you see, all the names are in sequential order, that is 1 2 3 4 5, so like this. So when we sort these two lists, so what happen is both the image and its respective mask would be in the same index number in the list. Okay, next we have split size. That this split size is basically how many images are 1%, that is 10%, not 1%. So we have split value and we have total length. So we have multiplied total length with the split value. So this means how much images would be 10% of the total number of images because these would be used to split the data set. Next we split this data set using train test split function, and we give it images mask, images path, and mask path, and we give it split size, that is how many images we want to split. So we got our training images and the validation, and same we have training mask and validation mask. So now till now training contains 90% of the data. Now we again gonna split this data, and this time we're going to create our test data set, and this way we have our training, validation, and testing data set. Now we'll work on a function which would help us to read the images and convert those images to patch size. patches, not patch size. So function name is read underscore image. It take a single image path. We first decode the path. We read the image as an RGB. Next, we're going to resize the image according to the image size we have set in the configuration. After that, we're going to divide the image pixels with 255, that is maximum pixel value. So what this would do, it would convert all the image pixels in the range of 0 and 1. Now it's time to convert this image to patch. So we have the shape of the patch is single patch. It's of patch size by patch size number of channels. Next, we are using a function from patchify library which take image which need to be converted to patch, a specific patch size, and this is basically a step value. Let's say our patch size for now, let's say, is 4 by 4. So here we set this patch size, and next, how many steps after you want the next patch? So we want 4 by 4, then after that we want 8. From 8 it should start. Oh no, not 8, that is 5. From 5, 6, 7, 8. Okay, so this is step size. So with this step size you can also create patches, overlapping patches, but for now we are not having overlapping patches. Then I'm going to reshape these patches to this specific patch shape, and this patch shape is basically number of patches. Then we have patch size into patch size by number of channels. Okay, and we change this data type to float 32. So this is the process. Maybe you can check this patchify library once and see its documentation. I know as a developer we don't see documentation much, but we should really check the documentation first. Next, we have a function called read mask which takes a path. So this function is really simple. We decode the path, we read the path as grayscale image, we resize it, and same, we divide it by 255. So this mask only contain 2 pixels, that is either 0 and a 255. So 0 indicate a background class and 255 indicate a main class, that is human hair. So when we divide its pixel value by 255, it would convert either to 0 or 1. So we're gonna have two values, 0 and 1, and we also convert it to float 32, and we expand its dimension on the 0th axis, that is starting. No, it is the last axis, -1 refer to last. Sorry. Basically, I also work with PyTorch, so sometimes I just mix both the TensorFlow and PyTorch. Next, we have few more functions which would help in the implementation of our training pipeline. So first is TF parse, and inside TF parse we have another function called parse which take x and y. X and y here refers to single image path and single mask path, and here we are using our read image and read mask path, and just give both the values, that is image which is now converted into patches and reshaped accordingly, and the mask. Next, because we are using NumPy and OpenCV here, so we cannot directly use both these image and read mask function. So what we do, we use tf.numpy function and we call this parse function which itself contain both these functions. We give the input, we need to give to this underscore parse function, and the return data type, that is float 32. We have specifically mentioned that here just to confirm. Next, we set the shape, and the shape here is the images of shape, the flat patches shape specified above. Next is mask. So mask is image size by 1. Next we have tf underscore dataset, and this is the last function which we're going to use. Rest all function come inside it. So we are using tf.data API, and it take list of images path and mask path, and we are using map function, and inside map we have called the tf underscore parse function which is going to read, resize and do all the functionality. Then we have batches, and we prefetch some batches in advance. Okay, so this is our training dataset pipeline. Now we're going to move on to the training part. First of all, we'll build our dataset pipe, that datasets pipeline using the tf underscore dataset functionality. So we have training dataset and the validation dataset. It take training images, training mask, and the specified batch size. Next, it take validation images, validation mask, and the specified batch size. Next, we're gonna load our model. Okay, so we have called our model and we have given it the specific file which contain its configuration. Now we're gonna compile it using the dice loss and the HDD optimizer, and we're gonna call the model load summary function just to check whether up till things are working fine or not. Okay, so things are working fine now. Now we're gonna have a few callbacks. So these callbacks would do few functions while the model is training. So first one is model checkpoint. It would save the weight file. Next is reduce LR on plateau. So it would decrease the learning rate accordingly. Let's say this your metric val loss does not decrease up till 5 epochs. So it would decrease the learning rate by a factor of 0.1 and it would not go below this. Okay. Next we have CSV logger. So during training you're gonna have your training loss, testing, and the validation loss. So it would record all that. And last we have early stopping. It's gonna also monitor your val loss. Let's say for a continuous of 20 epoch, loss does not decrease, so it's gonna stop the training. You can adjust these parameter accordingly. Let's say from 5 you can set it to 10, from 20 you can set it to 100. So this is up to you, it's your choice. And last we have model.fit function, and this fit function would do the training. Now let me start the training process. Hope it should start without any error. Okay, we have some things. So let's till then let's move on to the testing part. So again we're going to implement some libraries and functions here, and again we need that same configuration file from the above. So I'm going to copy it so that we have exact same values. Again, so from train we can have create dir also here. So what I'll do, I'll simply copy paste large section of our code. So first of all we're going to seed the environment with the same seed values. Next we're going to create a folder called result. So inside this result folder we're going to save our predictions. Okay, next we're going to load our model using the custom object, that is dice loss. Let me check the training. Okay, so training is being done, we can see. So let's train it for few epochs. Now we're going to load our data set because we need the testing data set. So this is done. Let me just change the path and rest things are fine. Now comes the main part, okay, where you're gonna move on to the loop where we have training images, training mask. So let me train it. So what I'll do, I'll just comment out this part because we still don't have the weight file, so it would give you an error. Okay, and the rest part would work, and we're gonna train it. Let it train. Let me zoom it a bit so that we all can see easily, even if you're using a mobile phone. Okay, let me activate my environment, TensorFlow, and let me. Oh, okay, one thing. We're gonna have a break. Okay, so our first thing here is to extract the name. So we have the path here. Let's say print x, small x. So I'm going to run this test out. py. So this is the path. So what we need is this name along with the extension. So this x is a string. So what we gonna do? So first extracting the name. So we're gonna say name equals to x dot split. And if you ever used this split function or no, so this is a string, and if you're gonna give this slash to the split, it's gonna split this string into a list. So let's give it this x, and we're gonna print name, and let's run it again. You can see a list, and the name may appear in the last. So we can say, so just remember that your initial path can change, but your image name would always stay on the last. So we can say -1. And if you are using Windows, please print this path and check the slashes. Okay, so they would be different for you. Most of you guys don't seems to understand that if you are using a window, the slashes would be different. Okay, one of the main difference in window and Ubuntu is that Ubuntu uses these slashes. I think these are called backward slash or forward. I don't know. I'm always confused with them. But just remember that slashes are different. So before any path you specify, just print them once manually and check them. Okay. That is the best thing you can do, and most of your error would be removed. Now we have both X, that is image path, and mask path. I've already explained you the process of reading image and the mask. So this is the process of reading the image, processing it to patches, and here we read the mask. Okay, now we need the code to make prediction. So you can see we have trained our model on at least one epoch. So what I'm going to do, I'm going to stop it now, because I need to write the code for prediction. I need the wait file, so I need to stop the training because I also need the GPU and if the GPU is being used by the training process, we can't run the test file. Okay, so we're going to make predictions, and this is the code for prediction. So we're going to give the patches to it, verbo 0, and then what we do, we predict, we have this pred, and we're going to append or concatenate it on the last axis. Okay, I'll just simply explain it to you why. Okay, so let me now print the shape, because shapes are important. So what my plan here is, I have the image. I'm going to first have an image, then I'm going to have this ground truth mask, and after that I'm going to stick this prediction. That is what I mostly do for better comparison. So the shape of all of them should be same. Okay, so that's why I'm making sure that they have same number of channel as the image. Okay, here you can also see this, and same thing I'm trying to do here. But let me print the shape of the prediction. Okay, sorry, should move on to the okay, just make a prediction. Okay, you can see. So because the input we have give is also batch, but this batch only contain one image. So what we say, let's do this, and we have a mask of 256 by 256 by 1. Okay, do it. I can see 256 by 1. Now what we do, we concatenate it like this on the last axis, and we change the shape to something like this. Okay, it takes some time. You can see shape changes. Now this make it easy to concatenate. Now what we're gonna do, we're gonna concatenate all the images in a specific sequence, and that would be, so first of all, the sequence image, we have a line in between them, we have mask, then a line in between them. So this is a fight line, and then we have prediction, and this is the path, and we save the image. That's it we're gonna do. Okay, and we also have, till now I haven't applied any thresholding. I just want to see how the result look without thresholding. So what it does, it convert the pixels in the range either 0 or 1. Okay, so 0 refers to your background, 1 refers to the human hair. But if you don't apply, it would be row value. So let me run this and check. I hope things are fine without any error, because sometimes I usually have an error while I load the weight file. So let me just stop them just to see a few samples. Okay, you can see, I can see that the predictions are good enough with one epoch as the training. So what my theory is, I've initially used another data set with small number of images, and with that data set things did not work out. So what I've understood is that if you're using transformer and that too training everything from scratch, even the encoder, so your dataset should be large enough. That's why I've used this dataset which contain about 2.9k images. Okay, so you can see the effect. Maybe you can do this ablation study on yourself. Just use, maybe you can use this dataset or another dataset with less number of images and then train it more number of images, and maybe you can see the difference yourself. But with, I can say, the one epoch, it's working really well. Now inside the files folder we have two files, that is weight file and this log.csv. So let me open this log.csv. So if you remember, we have just trained it on one epoch. Okay, why it is not coming? Okay, you can see it has four values: epoch, loss, lr, and the val loss. So it capture all these things, so this make it easy for you to study the things. Now what I'm going to do, I'm going to copy both the files. Even if I copy the weight file, that would be enough. Still, is this? Oh, my mistake. I've removed the original weight file. Ah, saved from an accident. Now let me again test it. So let me show you this file now. Again, it's opening on second desktop. You can see I've trained it until 50 epoch. Okay, this is 0, so 0 till 49, 50 epochs. And you can see loss, training loss start from 0.26 and it goes till 0.61. And the testing loss, or the not the testing, the val loss, you can see 0.21 till 0.077. So you can see it's decreased early, and you also can see the learning rate. So I think it has more scope to train, just that you should have the time to train it. And it's going to take around 2 minutes. So I can stop it and we can just analyze those samples only. You can see it's working good, but in some cases it does not work. Like in that case, it's working worse. Okay, at the edges it's working worse. So this does not give you fine results. So I think you need more data. You can train it on more images, apply augmentation. I don't even apply data augmentation on this data set. So you can use data augmentation and increase your performance. But still, as a demonstration of the training of UNETR, this is enough. I think you can use this code and work on yourself. So that's all for this video. If you still have any question, please comment down. And people also email me regarding their problems. So sometime, or most of the time, I won't reply, because see, I too also busy in other works. Okay, and you know my channel is not that good, so it's gonna provide me with the money, and I can take care of all the other financial need. So I just do other stuff also to meet my financial need. Okay, so I'm sorry for that. Maybe I don't reply to your emails, but sometime I try to help if in case I can help. Okay, so again, thank you for watching the video. If you really like the content, then please like the video, share it with your friend or on your social media. Maybe I can get few more views. Just that. Thank you. Have a nice day.